Okay, this is Chapter 2, Kinematics in One Direction. Now, when I say kinematics, what we're really talking about is we're talking about position, velocity, and acceleration. And I'm going to talk about two types of velocity, average and instantaneous. The change in velocity over time is acceleration, so we're going to talk a little bit about that. What does motion look like given a constant acceleration? Very important topic. We're going to talk about that. Solving problems for kinematics, also a very important topic. Freely falling objects, a perfect example of motion at a constant acceleration. And what do the graphs look like for linear motion for position, velocity, and acceleration? But first, we need to talk about reference frames and displacement or position. Now, choosing the reference frame is very important to any type of kinematic problem. Whether we're talking about position, distance, acceleration, we just need to choose our reference frame intelligently. So if we have a train, classic example, that is moving with a velocity of 10 miles per hour, and if I'm on the train, here I am, and I get up and I start walking towards the front of the train, and I have a velocity maybe of 1 mile an hour. If you're sitting over here on the train, you look at me coming towards the front of the train and you say, wow, that guy is coming towards me at 1 mile per hour. That is your reference frame. Now, if we have some fella out here on the platform, his reference frame is going to be very different. He's going to see not only me with my velocity traveling at 1 mile an hour, but he's also going to see the train traveling at 10 miles per hour. So he's going to see me moving to the right side of the screen with a velocity of 11 miles per hour. His reference frame is different than yours. So we need to choose our reference frames importantly when we talk about kinematics, and always choose the simplest reference frame. In the case of this example, you want to choose the reference frame of the train. I also need to make a very distinct difference between distance and displacement. So if, for example, you are sitting at a stoplight, so I'm drawing your car right here, and you want to pull into the local 7-Eleven and get yourself a Slurpee. Now, the 7-Eleven happens to be right over here. But in order to go there, you need to go up the road, make a U-turn, come back around, and pull into the parking lot. Now, your displacement is how far you are from the stoplight, and that's this blue arrow right here. Your displacement, in this case, would be 40 meters. The distance that you travel is measured along the actual path. So if you had to go 70 meters, pull your U-turn, come back around, your distance traveled would actually be 100 meters. So very distinct difference between the two. You could even say that the displacement would be path independent. We can write our displacement simply as the change in our position. This is the Greek symbol delta, and what it really means is change. It means the final position, x2, minus x1, being the initial position. Now, just a heads up, I may occasionally write this as final minus initial. The book uses 2 and 1 because it says, hey, that may not be your final destination. You may keep on moving. I tend to think of these as final and initial. Now, we can have positive and negative displacements. Remember back to our days of algebra, we draw our axes with positive sides and negative sides, where typically down is in the negative y direction and to the left is in the negative x direction. So if our displacement goes from, say, 10 meters to 30 meters, then x2 is 30 and x1 is 10. So our displacement would be positive 20 meters. That means I've moved from the left to the right towards the positive x direction. Now if I move in the opposite direction from the right to the left, then my displacement, x2 minus x1, where x2 is now 10 meters and x1 is 30 meters, then I get negative 20 meters for my displacement. All the negative sign really means is I've moved from the right to the left. Now just to note, the distance that you've traveled is 20 meters in both examples. So distance doesn't really have a direction associated with it, however displacement does. Key difference. If you change your position over some time, then you have some speed or velocity associated with that. And we typically write that as your average velocity is going to be the change in position divided by the change in time, where this would, as on the last slide, be x2 minus x1 divided by t2 minus t1. And similar to the caveat I mentioned on the last slide, distance does not have any direction associated with it, therefore neither does speed. You can say that my speed might be 10 miles per hour. I'm covering 10 miles in 1 hour. However, you're not saying which direction you're going. Velocity, on the other hand, it does. Displacement does have some direction associated with it. It matters if it's positive or if it's negative. Therefore, velocity does also. You would say, therefore, I travel 10 miles per hour to the east. That would be a velocity. 10 miles per hour would be a speed. Now, instantaneous velocity, if we think about our change in position and we divide that by our change in time, I can maybe draw an average velocity of 40 kilometers per hour for a half-hour interval. And over here I'm going to draw a dotted line with that. Now, in reality, we don't actually travel at a constant velocity. Say if we're getting into our car at our house and we're initially at rest, and then we get our car up to the interstate and we start doing 60 kilometers per hour, and then we may slow down, hop onto Route 11, and then pull into the grocery store. That is maybe a more realistic view of our velocity or speed. Now the average velocity for the trip, if you know that you traveled 40 kilometers and it took you an hour to get there, your average velocity would be very well described by this dotted blue line that I drew. However, your instantaneous velocity is very different than that. Instantaneous being as the time interval becomes very short. So maybe we're not talking about the full half an hour for this trip. Maybe we're talking about 1 minute, or maybe a second, or a quarter of a second. This change in time becomes very, very, very small. And so we can look at smaller time intervals, and we can see right here that our instantaneous velocity might be 60 kilometers per hour. Over here, in the same time interval, it might be 30 kilometers per hour. And as that time interval gets shorter and shorter and shorter, just picture me drawing smaller and smaller slices, we get a better feeling for what our velocity is at any given instant. Now, if we change our velocity, then we are accelerating. You know that if you, for example, you're at a stoplight and you start moving. Initially you're at rest, and then you punch the gas and you're moving 60 miles an hour. It's a change in velocity over time, and it doesn't necessarily need to be the velocity increasing. If you are, say, moving and then you apply the brakes and then you come to a stop, you've gone from, say, traveling 60 miles per hour to the east to 0 miles per hour. You have changed your velocity, therefore you have accelerated. Also, if you're going 60 miles per hour to the east and you grab hold of the steering wheel and you go to 60 miles per hour to the north, you have also changed your velocity. You haven't changed your speed, but you've changed your velocity, you've changed direction. All of these are changes in velocity, therefore all of these, by definition, are accelerations, which is a change in velocity divided by a change in time. Kind of to highlight it, again, acceleration is a change in velocity divided by a change in time, or velocity 2 minus velocity 1 divided by time. 2 minus time 1. If my initial time is equal to 0, this boils down to v2 minus v1 divided by time. If I am, say, accelerating at 15 kilometers per second, as we are right here, noticing now that there's some interesting units going on here. We have kilometers per hour divided by a second. After 1 second, and my initial velocity is also 0, so I can just write this as velocity 2 divided by time now. At t is equal to 1 second, my velocity 2 is going to be my acceleration times time, or 15 kilometers per hour per second multiplied by 1 second. Noticing now that the units kind of cancel out and we're left with 15 kilometers per hour. At 2 seconds we can apply the same logic and we get 30 kilometers per hour. And at 5 seconds we're traveling at 75 kilometers per hour. Again, acceleration is a change in velocity divided by a constant measure of time. So it's no surprise that we're going from 0 to 15, 15 to 30, and then after 5 seconds up to 75. Our velocity is changing as the time goes by.